Well, thank you very much. Thank you for being here. I know that you have a very long trip yesterday. So we'll continue, and today I'll switch from one driven phase transition to another one. So first lecture was about the binning. This one will be about the yielding transition of amorphous solids. And I will talk about criticality and avalanches associated to this yielding transition. So again, before I forget to thank people, listed here are people with whom I collaborated in this topic, which started when I went to the group of Jean-Louis Barra in Grenoble to do a postdoc. And of course, I mean, I mostly worked with Jean-Louis and Kirsten, but also with all these people here. The other day, talking with the students, someone said, well, okay, we are here in the school of disorder system, but so far nobody has defined what a disorder system is. So I guess that there are many definitions depending on where you come from, or what is your systems under study. But in this case, it's quite easy to define why amorphous materials we call disorder systems. It's simply whatever material where these elementary constituents are not arranged in an order geometrically. It's non-crystalline, okay? Amorphous as opposed to crystalline. So all these materials that you can see here, ranging from grains at the big scales through foams, emulsions, gels, etc., to atomic structure like the glasses, metallic or silicate glasses, as you have seen yesterday, are structurally disordered. But they share common properties, and in particular when we try to deform them. So they are solid-like, so-called elastic response when you try to deform them gently. Even a foam you put in your hand, it maintains a shape, and it will come back if you touch it slowly. But if you deform hard enough, it will yield and flow. So they behave on one hand like a solid, and on the other hand as a liquid, according to the deformation that we try to impose on them. And then, of course, we could classify them on which of these materials is more sensitive to temperature. For example, on this side, we have diathermal systems. In this side, these are much more thermal. Of course, depends on the size of the grain. And how much they are viscous, for example. Here is if they are underdamped or overdamped, okay? How much they respond to inertia. So there are two reviews, well, there are many now, but at least one extended experimental review on the amorphous materials that you can find in this reference. And we have been building in Grenoble another one related to elastoplastic models that I will talk about today. And this figure is taken from there. So yield stress systems, as I said, they are characterized typically by this schematically, no, by these two curves. The first one is stress as a function of strain. So as I said, if you deform gently, there is a linear response, just as a Hookean solid of the stress as a function of strain. And mu is a shear modulus, for example, if you are doing simple shear. But eventually, this arrives to a plateau where the stress stops growing and you are in a plastic flow. But if you do this at different velocities, different strain rates, velocities of deformation, this plateau changes. The steady state is at higher and higher stresses. And with this, you build this so-called flow curve, okay? Or Escher-Buckley law. So a yield stress material, it has a viscosity that depends on the shear rate, in a sense, as opposed to a Newtonian fluid that will be a straight line, okay? So you have a behavior that when you decrease the strain rate, You don't arrive to 0, but you arrive to a finite value that's called the yield stress, okay? And with this picture, we'll build the yielding transition. To show you some examples from the real life, so these are stress strain curves for very different systems, but you see that they have the same more or less same shape. This is for a foam. These are many different metallic glasses. And this is a carbopol gel. Carbopol is a polymer. So this is, for example, the hair gel has this carbopol polymer. And here you can see that here there are different strain rates. And you see as the strain rate goes up, the plateau is up. It's bigger and bigger. And here below, some flow curves. This is an emulsion with different droplet sizes. So again, the critical point or this yield stress is non-universal, as it happened for the critical force in the pinning, if you remember. But then there is the idea that the critical exponents will be universal. And here again, the carbopol gel for different wettability or different dilutions, okay? In fact, it's seen in the literature of rheology of these systems that typically the exponent n of this Escher-Buckley law is around 0.5. And some people fit it and report it. And some others say, no, it's 0.5 and just fit the rest of the things, okay? And it goes quite well. So there is the idea that there is a kind of universal exponent for the flow curve. If you put it, okay, we'll see this later. Of course, what I've shown you so far is quite the nice and easy cases, but stress strain curves can be much more complex. You don't always have this. In fact, if you take hard or brittle systems, eventually this just has a failure and you don't see any plateau, okay? But there are things that are hard, but are still ductile, as metallic glasses. I think you have seen metallic glasses yesterday. That in fact you start compressing this and it's like melting, okay, instead of breaking. And it has a plateau of an average stress where we can see avalanches, etc.
Can you come back on slide?
One or two.
Could you give us a little bit of intuition? So the first line means that you apply a strain, the first, and then it would come back. You have an elastic region here, right?
Yes. Yes.
And then at above a certain strain,
you start having irreversible plastic deformation.
I see.
Okay?
So the material.
So this is yeah.
And this is but this is actually an average, right? Because the material.
Of course, you'll see. I mean, all the physics we will tell about today is related to the jerky plateau here, okay? But yeah, so you're right. So here you have elastic response. It will come back. After this point, there is irreversible deformation, and you can keep deforming, and it will keep. So you cannot keep deforming any material forever because it breaks. But the emulsions, the gel, etc., you put it in a rheometer, which just turns. Geometry is confined. The material will be always there, so you can keep deforming as much as you want. Okay? So as I said, there are further complex stress strain curves. And for example, it's not that you have always a just straight line and another straight line, but typically there is a bump, and the height of this bump or overshoot depends on the aging of the system. So more aged systems have a larger bump, but still the steady state you can always measure this plateau, for example, for this here suspension. There are materials which also with age changes their internal mechanical properties, and then even the plateau can depend on aging. And yes?
What does it mean to age the system?
Just wait, as Leticia was mentioning in her lectures. So you are prepare a system, it's out of equilibrium. You are at a certain finite temperature or whatsoever. So the system will still reaccommodate, okay?
So in grains, for example, do we have to let the grains
No,
sit
well,
there for
grains which are monothermal are aging less, but so in all these suspensions or gels or whatsoever, there are particle movings, bonds of the gel network forming and breaking. Eventually things get more and more complex. We will see maybe tomorrow that in grains, there is the idea that also systems are aging in soil, for example, but it's very, very slow. And so far, we have no clarity on how is this happening, but yeah, some people will tell that everything ages, okay? Okay, and finally, then if you have some polymeric systems, this could, when you keep deforming, you eventually start to track other bounds, more stronger bounds in the networks. These polymers are, well, networks of links, and eventually you create stress because you deform more, and this is called strain hardening. So, of course, this is just to give you an idea of the jungle of reality that are in these systems. We will focus on the cases where people can do experiments and extract a given portion of this stress-strain plateau and measure properties of this signal, okay? Because actually the idea is that you load the system, the stress wants to go up, and then it yields, it cannot sustain more stress because some region rearrange, and this triggers another region to rearrange, et cetera, and these are avalanches of plastic events. And avalanches of plastic events are measured in many systems, foams and granular systems, bulk metallic glasses, very different nature, but they all show more or less the same physics, that there is a power law distribution of avalanches. And then the discussion is there some kind of universality, if a phase transition is behind all this, okay? So we will talk about this today. So as I said, there are many definitions of yielding. I will mention in a minute others, but I like to think the yielding transition as what is written there. And look at this. I mean, we have the flow curve that people actually measure in the lab, and it's typically the steady state of stress as a function of the log of the strain rate. That's why it looks like this. But if you take out the log, the curvature will change and will be a curve like that, okay? It's still the same function, just in linear. And now if we switch the axis and we put strain rate as a function of stress, we have this curve, okay? And this is a bit odd because we like to see things like this because we're coming from statistical physics and we know the phase transitions are like that. But this is exactly the same functional form for a singular behavior of an order parameter as a function of the control parameter. Now, gamma dot will be the order parameter, and this will be the control parameter. It happens just that arrive with an exponent b that is bigger than 1, okay? And this is the yielding transition defined in the way we know in statistical physics, if you want. As I said, there are other definitions, and there is a community of people that is discussing very strongly, because there are different views, etc. As always happens in this field, about yielding as the onset on stability. No, when you go out from the elastic response and go to the plastic flow, and there it is known that if you prepare the system in a very well annealed sample, you will have these big overshoots. If the system is poorly annealed, it will be smoother, and so you have continuous transition or discontinuous transition according to the initial preparation of the sample, which I don't like very much to define a phase transition, but okay, I mean, you can, and there are analogies also with the random first order transition, as Letizia was presenting the last days. So this is another definition of yielding, and there is a recent review by Ludovic Berthier and others in the archive. And one way of getting rid of this dependence of the initial condition is actually to do oscillatory shear and arrive to steady state for every amplitude of the deformation, okay? So here I'm showing for example, these curves are the same as here. That depends on the initial condition. But then you can do this oscillatory shear to different amplitudes. And what happens is that if you are still in an elastic branch, there is a mechanical annealing of the system, and the steady state at this amplitude goes up to here, up to the same curve, independent on the initial condition, and then eventually breaks. Okay, here it breaks. So there are other definition then of the yielding transition according to the shear annealing protocol, oscillatory shear annealing protocol. Okay, but I mean these two are just for completeness because we are going to define yielding as this. Okay, and of course there will be critical exponents related to this transition, the one of the flow curve and the ones related with avalanches, and also something that is new that we didn't discuss in the pinning the other day, and that is related to this density of shear transformations. So let's start with the modeling. And sorry, but I need to drink because otherwise, no, my mouth is. Yeah. Typically, there is someone who helps, no? No, yeah. Take, please. Me das uno cada tanto. So, elastoplastic model of amorphous solids. Tell you about the two basic ingredients for the modeling. So the first ingredient are local rearrangements. These are called T1 events in foams. Okay, foams is very well known what geometrically a T1 event is. So first you have these four bubbles in this configuration. These two are touching, these two are not touching, but eventually then the two whites move apart and the blue ones start to touch. Okay, and you see it in this video by Martin Van Heck. So the idea is that, as I said, that these stress drops are produced by many of these rearrangements that correlate. In general, in other systems that are not foams, there are not just 4 particles or bubbles which are involved in the transformation, but many, dozens or even hundreds, okay? So, local rearrangements. In the second ingredient is the medium elastic response to these local rearrangements. Maybe in the video you see, but each time there is one of these T1 events, it's like the whole foam is shaking a little bit because this goes long range. And it has been seen in simulations, but also in experiments. Each time there is a local rearrangement, the rest of the system feels it, okay? Of course, feels it more intensely close to the event than farther away. But here, for example, you see in a molecular dynamic simulation the map of displacement and the stress change, okay? That has positive and negative lobes, okay? And I will talk about this a bit more. But this is very characteristic. And as I said, it has been measured also in emulsions, in colloidal glasses, and very interestingly, not only when you are under shear, but also in quiescent systems, okay? And all this happens in the different systems because these are very, very particular, well, not very particular, very general property of the problem of deformed inclusion in a elastic matrix. Okay, so you take an elastic system, take a piece of it, for example, a circle, deform it into an ellipsoid, and then plug it again. You will produce some stress, and the response is the so-called Eshelby propagator for the stress redistribution. The stress along the system will be distributed like this, with an intensity that decays as 1 over r to the t, so it's dipolar in range, but it has this particular cosine 4 theta on the numerator, which is this quadrupolar in symmetry. So I should say probably what is theta and what is r, but so suppose that you have your sample here, and you are doing this shear, no? Like this. And something happens there. So this is a plastic event. and you want to see how the stress in this point is affected, okay? So basically, theta will be this angle, the angle between the direction of shear and the vector that connects the two places, and this will be R, okay? So, okay.
Let me ask you something
Sure.
here.
Well, tell me.
Yeah. In models, in vertex models or confluent cell tissues, for instance.
Sorry, what?
Vertex
Vertex
models,
models, I understood.
For confluent cell tissues.
Yes.
For instance, you also have those local rearrangements, that
Yes.
first ingredient that you
Yes.
mentioned.
Yes.
Do you also get the same kind of a Shelby propagator in that kind of model as well? How
when you do
robust?
the coarse grain, yes. Also, in fact, the idea is that even when you don't plug this propagator in the models by hand, if you have a model that is dense and then there is elasticity, in a sense, this emerges. Okay, so confluent tissues models, if you go and do a deformation, measure response, if you do one deformation and measure the response, by any chance you will see this. You will see something. But if you average a lot, and this is what people do in molecular dynamics to get the full propagation with all lobes, positive and negative, this always.
So this is
appears.
very general
It's very general.
of yielding transitions.
I mean, it's very general.
Doesn't depend on the particular
Very
foam
general
or
of elastic
tissues
mechanics. No, does not depend on any detail of the models, and it
So-
works very well.
My question is very related to the ones that Danilo asked, but I would like to just to add one question. You need to be very dense, right? For example, if I go in direction of the
Sure.
jamming point, Z equals to 4.
No, absolutely. I mean, this is something important that I didn't tell you in the first slide. The yielding transition is a transition with the stress. Of course, if you dilute the system, eventually things start moving because the system gets below the jamming. All this is at very high densities, and the only way you can make things flow is by mechanical effort. So we will build these elastoplastic models, we said at a mesoscopic scale, okay? What is this scale? Well, we want to make a coarse graining big enough such that there can be a rearrangement inside the cell, containing as many particles as I need for a rearrangement, but not more than one rearrangement, okay? I want to be at the scale of individual rearrangements, and then this is what we do. So you take a lattice, say, okay, in this material, the rearrangement are this amount of particles, and then this is the idea. This is the mesoscopic scale in which we work. And after that, then it's just like a model, no? And Matteo already mentioned elastoplastic model in his first lecture, but let me just recall you a little bit how it works. At the end, we have a lattice of values of stresses. Also, another simplification is I'm taking just one component of the stress, the shear stress, so it's scalar, okay? And all these blocks that bears a given stress are stable, we'd say, below certain threshold. So they are responding just elastically. But if the block goes above its threshold, it will yield, okay? And what it means to yield, locally, this stress will go down, and then it will cause stress changes in the rest of the system through this HLB propagator, okay? And so in order to define the system, we need not only the stress, but also the state of the block, if the block is still stable or not, okay? Or we call non-active or active. And then we have an equation of motion for the stress as a function of the strain rate and the states of the stresses. This is a global loading. It will stress all the blocks. When one block activates itself, this n goes from 0 to 1, and then there is an exponential relaxation of that block, of the stress on that block. and then it receives mechanical noise or kicks from every other active block in the system. The JIJ is the Shelby propagator. And as I said, we need to complement this with the local rules for yielding. Here they were depicted, but again, when no one is active or yielding, they are 0. And when a site yields locally, it becomes 1. And this happens typically when it overcomes the threshold. And then we can immediately turn it off again, or we can say it will be yielding for a given characteristic time, okay? So here is depicted in this way. For example, here, in this model, you need to be above the threshold, and there you have some chances of being activated with a rate 1 over tau on. And then when you activate, you will be active during a rate 1 over tau off. So we'll talk more about elastoplastic models in the lecture. And they have come up to be useful to interpret real experiments. In fact, these are phenomenological models that come from the rheology community. They were not intended to study phase transitions in particular, but to fit curves, okay? So people have fit real emulsion curves with these models, discovered that there could be shear localization to explain shear bands and other things that people see in the lab by changing the parameters of the models. Relaxation in yield stress systems, where we have been working with Heber as well in this. And the movement here in a narrow channel, the profiles of the flow in microchannels, etc. This is just to say that there are many things we described in the review. But now I'm interested in this. Okay, phenomenological, they can describe many systems if you tune the parameters, but they are also good toy models to do theoretical statistical mechanics and study phase transitions, where typically we put every parameter equal to 1 or things like this, okay? And then we'll go to discuss about avalanches.
Oh, sorry, can you?
Yeah, go.
About those models, you put it by hand, this SOBI propagator.
Yes.
But
then you have on many other parameters, no?
Right. But my question is, at the large scale, can you see again this pattern of this fourth? I mean, the pattern that you showed us. That is
yes,
very
yes.
common.
I mean,
you recover that.
If you are putting it by hand, of course you have it.
Okay, so it's trivial. It's trivial in that case.
It's super trivial. Yeah. I mean, you take down your system and you take the site in the middle and you activate it and see the response. You are putting it in the equation. Yeah. It's the SUP. Okay. So, yeah. No, of course. Yeah. They recover that.
Ezequiel,
yes.
Sorry, in the previous slide, is this model containing a velocity or some velocity of propagation?
No,
it takes time to propagate.
It's overdamped. Okay.
Okay.
So the system, this is an overdamp here, but there's a friction.
But I mean, if one side relaxes, will it trigger immediately something in the other side of the system?
Immediately.
On the other side, okay.
Immediately. This is an approximation. I mean, overdamp. This is an approximation. I will talk about inertial avalanches later on, and there you have to go to final element methods kind of simulation. Okay. Yeah, of course, this approximation is bad for many situations, but in general, it works for the statistics. So we'll talk about avalanches and what is an avalanche. As I said, you take the stress time series or stress strain, which is the same, and you detect where the derivative changes basically, and the stress is going down, and this is an avalanche or a stress drop. More general speaking, the stress drop, and it has some duration. It starts there and it ends there. So this will be the duration of the stress drop. And we can talk about the size of the stress drop or the size of the avalanche as the stress drop itself, the delta sigma, times the system size, okay? And then you can also define shapes that I'm not going to talk about today. And you can go, in a model, of course, you can go to a quasi-static case where gamma dot is taken to 0 and you deform until the next instability occurs. And everything that comes after this instability, this first activation, you are for sure that it's correlated with the one that you trigger first. So this is actually where avalanches are well defined in the quasi-static limit. All the rest is what we can measure or what we can do, but let's call them stress drop instead of avalanches. And there we will be interested also in quantities as this X mean or delta gamma is how much I need to push to have the next avalanche. Once avalanche is finished, which is the distance to the next instability. Okay? So people have worked in this in many different elastoplastic models because, okay, there was the idea that avalanches in the experimental system should be like mean field depending like any other thing in avalanches seen in many systems. But in using elastoplastic models, people started to realize that the exponent is not 1.5 as we expect from the mean field depending, and it's smaller. And okay, I mean, there are some variations, but there was consistency at least in the fact that the exponent is less than 1.5. And okay, I will maybe skip the details of this because I mean you can deform in many ways to get the avalanches. But for example, these two are similar to what I showed you for the depending avalanches algorithm of Alberto Rosso, that you start below the critical point, you are stuck, but then you increase little by little forces or stresses in this case, controlled by a spring, and then you see one avalanche finish, then you push again, see another one, etc. Okay. The consistency of the exponents went beyond simple shear, but many different kinds of deformations showing exactly the same. Power law, even fitted with a generalistic formula where you have only one free parameter. And apart from this exponent being smaller than 3/2 or close to 1.3, another thing is that people observe that the avalanche's fractal dimension is close to 1. Here we are in 2D. So avalanches in yielding, instead of being compact objects like a bubble which has a fractal dimension similar to the one of the space, are more slip lines. Okay, these are pictures of avalanches. They can be even disconnected. This is the same avalanche. Okay, but the activity started somewhere here and then created this slip line. Because of the long range, another side here was triggered and created this another one. Okay, so but the fractal dimension of the avalanche is close to 1. And what is a fractal dimension? You take different system sizes, distributions, and try to collapse them, putting here S, so the size of the avalanche, divided by L to an exponent. And this exponent, so L is the linear size of the system. This exponent is called the fractal dimension. So we took, with Eduardo Hagla, many models from the literature, as you see, with the rules that are depicted in these sketches. Some of them have a finite duration for the event. Some have, the events are just instantaneous. Okay, some of them yield as soon as they touch the threshold, etc. And we duplicated this because they say, okay, apart from these three that has a typical constant rate once they have been instable, they have reached the threshold or overcome the threshold to be activated. And we say we will consider this case, but also the case where the rate at which locally the block will yield is now progressive, meaning that if the block is more stressed than the threshold and is going farther and farther above the threshold, it should have a higher probability of yielding, okay? And this is the case. So we have in total 6 models. And we simulate the avalanches on these 6 models for different system sizes, collapse the curves to get the fractal dimension. And we observe that in all the 6 models, the exponent is the same, and we get 1.33. So when you do things systematically in the same way for different models, the details of the models do not matter for this exponent. And okay, so this was one result, meaning
so
yeah.
that's very interesting, but let me ask you a question. The only ingredients that you need to put, you say the tails doesn't matter, but you keep having an elastic regime and then some crash. It doesn't matter how do you put the crash, it happens the same.
Yeah, okay, so this is what happened for each local site,
Right.
okay? The elastic response of the whole material is somehow emerging from this that we have. So yes, so here we are using the same bulk modulus, if you want, for the elastic part. Otherwise, this slope will be different for different models. But what I mean, what you are changing the rules for yielding, and the rules for the duration of the plastic events. So for example, here there is not even a duration of the plastic event, but this event will finish when there is some amount of plastic deformation accumulated locally, for example. It's not based on time. And okay, and then we have this. So what will be modified in the tau, because the exponents of the avalanches, because when other people simulate, they get a slightly different one, okay? One thing I haven't told you is that since we have here a long range interaction, solving this in real space is hard. And typically what one uses is a pseudo-spectral method, because this propagator in Fourier space gets local in the Fourier components, okay? So this in Fourier space, it just depends on the local Qx and Qy. And so you can solve it in a step and then anti-transform to get the response in real space. But this is for Q different from 0. For the 0 mode, you have to define a value. And this value, typically, if you put 0, the system will conserve stress. In this case, as soon as you touch something and create some movement, then this avalanche will go forever, because you will be always at a stress bigger than the yield stress. You don't allow the system to do this jerky motion of the plateau. So typically one controls strain, and here you can put k equal 1, okay? And this is a strain control protocol. But this is just a convention, and you could use different values of k, which is the propagator in the 0 mode. And when you change this k, what happens is that this exponent you see, the effective exponent that you can fit, is changing. Here is closer to k equals 0 when you cannot stop the avalanche very easily, because you are not dissipating enough stress, and this is when you dissipate more, and here we see this variation. Of course, at the end, this all should be a finite size effect, and there is a scale below which all these things should be the same. But basically, if you are closer to k equals 0, you need to go to bigger and bigger system sizes in order to move this bump out, okay? So people have not been very systematic with these choices, and that's why we see some variations in the exponents tau. This is what I believe. So now I'll show you stress drop size distributions. Why stress drop size and not avalanche? Because we are in a finite gamma dot, okay? The smallest that we have here, but it's still finite. And we have compared here results of molecular dynamic simulations, where you don't put the Eshelby, it's just the particles and dense system, and you shear. These are the gray triangles. Again, different system sizes, then collapsed here for 3D, for 2D, and we see consistency with the elastoplastic model. In one way, we are validating the elastoplastic model with molecular dynamic simulations. And for 2D, we were finding in this early work the exponent 1.28, and again, a fractal dimension close to 1.
Ezequiel,
Yeah.
that for me is not very intuitive, because you said that this propagator decays with R over D, which means that in 3D it decays much faster than in 2D, right?
Yeah, but you have 3D.
Okay, no, I agree, but I mean, I would expect that the size of the avalanche would be different, no? Because, I mean, it decays, the longer range interactions that you have in 2D
Yes.
is much smaller in 3D, so.
And the size, you mean the
even
absolute value of S?
No, even the exponents are pretty much the same, no, in both dimensions.
Well, yeah, no, well, yes, yeah.
Isn't it somehow surprising that you have no difference?
No, I mean, there is no, the exponents, I don't expect them to be the same, because tau will depend on the dimension. Then we can discuss what it should be. But I think, in principle, is decreasing towards something closer to 1 in an upper critical dimension. This is at least what we have. And here you can see that clearly the fractal dimension is changing. So
Okay.
1.3 versus 0.9, because, of course, I mean, but this you should compare with 3. So the avalanche, the fractal dimension is still much smaller than the system dimension, but it's growing with the dimension. Okay. So, and I showed you that because now we will push with the gamma dot, bigger gamma dots, and we'll see that, that now the distribution in fact will change. So if we go apart from the quasi-static limit, the distributions here in 3D I'm showing you go from 1.25 to 1.5, so they change the slope. Here I multiply by 1.5, so you can see that the original one was here at a small gamma dot, and then goes closer to this flat line, which corresponds to 1.5. So there is a crossover of exponents when we increase the strain rate, and we will try to understand why. We can also measure avalanche size, avalanche duration sizes, okay, or stress drop duration sizes, and relate the duration with the size, okay, with this. So we see also for the duration a power law cut off by some fastest function, and the cutoff is controlled by gamma dot. So the TC here that cut off this power law is gamma dot to a given power that we can understand where it comes from, but I need to jump that. And then, as also I showed you for the pinning, there is an exponent relating the size of the avalanche with the duration of the avalanche, and this exponent cannot be another thing than the fractal dimension divided by Z, the dynamical exponent. So we expect this, and in fact we observe that, but also we know the dependencies of the prefactor in L and gamma dot, and the complete scaling is something like that, okay, with delta 1.6. So in order to understand why this is changing when you increase the gamma dot, I need to introduce now this emergent property of the signed propagator, or the SLB. As I told you, in the quasi-static limit, after one avalanche has finished, we need to deform again in order to trigger the next one, okay? And this was a key observation first in molecular dynamics for these systems. That the rate at which the plasticity occurs is not extensive. What does this mean? I mean, typically in a model showing this punctuated dynamics, etc., you expect that the amount that you have to deform until reaching the net stability should go as 1 over n. Meaning, if I double my system and I have more sites that are prone to yield, then I should need half of what I was imposing before to see something, okay? In other terms, if you are deforming at a given rate, yes, you shall write something, and you see some frequency of plastic events, now I duplicate my system, this frequency should double, okay? Because there are more. It's not what's happening. is sub-extensive, meaning that this distance that I need to go until triggering is going as 1 over n to the phi with an exponent between 0 and 1. In other ways, a system of double the size is more stable than the system of the original one, okay? So Mathieu likes to say 2 blocks of mayonnaise are more stable than 1 block of mayonnaise, but this is a property. And we can understand, okay, you understand with this picture, these are the blocks, the xi, these are the distances to local instability. And when we are loading, globally loading, we are pushing all the guys towards the x equals 0 boundary where they become unstable. And when they become unstable, they are reinjected here, okay? But also, when they become unstable, they give kicks to all the rest. And these kicks are positive and negative, okay? So they could unstabilize others that are here close, but they will stabilize the ones that receive kicks to the right. They will push them away from the boundary. So there is somehow a forecasting of this absorbing boundary that you cannot have if you don't have the sign on the propagator. If each side that is unstabilized pushes all the rest of the guys with him towards the end of the cliff, then what you will observe is just a straight line here for the distribution of distances to the threshold. But for the signed kernel, what happens is that a pseudo gap appears. And if you have this pseudo gap, you can explain why the x mean is sub-extensive because it's related with this exponent. So we'll mention again the p of x. So, we also do the statistics of the x mean for these our 6 models, and we observe that's a function of L that is a power law with an exponent 4/3, so it's n to the minus 2/3, and exactly the same that is observed in the molecular dynamics. And in fact, there is a relationship between this exponent and tau, because if you are in a plateau, everything that goes up should go down. On average, should be the same. X mean and the stress drop should be the same. So x mean, we said, is L to the minus d to this power phi. And then the stress drop is the size of the avalanche divided by the volume. That if it's a power law of this way, the average value, it will be df times 2 minus tau. Okay, and this is the minus d coming from there. So there is a scaling relation between tau, ddf, and phi that is pretty much well validated by the numerical values that we have. And these are 3 universal critical exponents. I mean, we have done 6 different elastoplastic models, and they look the same. So I may, well, I don't know. I will just mention one thing about this slide. That's why this is yellow, because if I'm lacking time, you shouldn't tell it. But this being just p being x to the theta, this distribution of density of shear transformation or distribution of distances to yielding, is an unnecessary simplification. And of course, if you propose this as an ansatz, you get the n to the minus phi with phi between 0 and 1. But the observation is this one, and this does not imply that p of x should be x to the theta. So after the proposal that was, in fact, by Mathieu and his group, many of us have found that the p of x is more similar to something plus s to the theta, so at the end there is a plateau. And what controls phi is the scaling, the finite size scaling of this constant here and not the theta. But okay, we are still discussing that. So we come back to this, the case of a finite strain rate, and as I told you, tau was changing. And why this tau is changing? Again, now we know about this property of the P of X, and let me put then the equation of motion like this, where I consider that this is just a noise. Okay, we could in fact replace this propagator times n and sigma by a given noise, and this noise is statistically measured here. Okay, for different strain rates, and you see strain rate is growing in this direction. When the noise is bigger, this distribution of noise is wider and wider. And it happens that this is what dominates positive and negative kicks when strain rate is big enough. As you go, sorry, I have to think here to don't say it in the opposite way. Yeah, okay, but eventually, gamma dot will, okay, this is a straight line showing how gamma dot goes. Gamma dot goes linear with the gamma dot, of course, but this width is not growing linearly with gamma dot. So when gamma dot is big enough, this term will win over the width of this thing, okay? So the external drive will win over the positive kicks, no matter if they exist or not. So they will take the case from a finite value of theta to 0, to the flat, as I show you. And then the exponent also goes to the mean field exponent of the pinning, which is the 3/2. And this was the explanation. So the drift dominates at big enough strain rates and changes the universality class. And so now I want to mention inertial avalanches, and then I will briefly also mention thermal avalanches and avalanches in active matter. Is this finished? And as I told Luis before, if you want to have waves, inertial waves, and sound velocity, a more realistic thing, you have to go out from the overdamp assumption and actually go and solve the Newton's equation, okay? So without entering into the details of the model, this is what we have done here with Kamran Karimi and Jean-Louis. We use finite element methods. So you have a grid, you do it irregular to be anamorphous, and on each block you will solve this equation of motion for displacement and the stress. Here the Eshelby propagator is not plugged in, it emerges from the dynamics. But basically the stress will have a restoring particle and a dissipative part. One depends on grad of u, another one grad of u dot. And the dissipation coefficient gamma is what is telling you how much overdamp or not you are, okay? Lower eta, so lower gamma, means more inertial. And here we compare, again, molecular dynamics with our finite element methods to show an overdamped and an underdamped stress strain curve, and I mean, qualitatively it's pretty well. But if we are adding to these finite element method models the rules of the elastoplastic models, in the sense that the restoring part, the part that responds elastically, will be on, but will be on when n is equal 0. When n is equal 1, meaning that the site has to yield, mu will be 0. So we cross out this term when the site is active. Otherwise, it's just the elastic modulus. And interestingly, what happens here, we are going from overdamped, what we have before, to underdamped, so more inertial avalanches. And what you observe is that there is a bump that develops and eventually a peak, a new characteristic size for the avalanches. So, and also the tau exponent changes, okay? So inertia is completely destroying our avalanche universality. and making this disappears there. And we want to understand a bit more what's going on there. If you plot the P of X, so this density of shear transformation or the distances to local yielding, we have the green curve for the less, so for the most overdamped system. And it's like the gap increases when the avalanche is more and more inertial. And this means, I mean, this makes sense. Meaning, before, we have sites that are close to the local yielding. One yields and brings the ones that are close with him, and this is the avalanche. When you have an inertial avalanche that goes on for longer and longer, it will eat more on this line of values close to the boundary. It will take not only the ones that are very close, but many of them, and then they will create this steeper P of X. And then we can plot also the P of X mean. So this is looking to all the blocks of the system. This is only looking to the guy who initiated the avalanche. For many, many avalanches, then we have this distribution. And the P of X mean, it was again like X to something in the overdamped limit, but in the underdamped limit, it becomes actually a bimodal distribution, separating two peaks with a value that I call somewhere X cross, okay? So we have these ansatz, that this X cross separates two kinds of different avalanches. Ones that look more like the overdamped avalanches that we already know, and others that are completely inertial. And, okay, it's just what I said. So we go and test this. So this is for different dampings, and we have the X cross for each of them. It's easy to detect the X cross for small values of gamma, so large value of gamma to the -1. In other cases, it's not that easy, but well, you can do. And then you go and separate the original distribution, complete distribution of avalanche that you have in two contributions, because you can go for each avalanche, you say, which is the X mean that has triggered this avalanche, or which is the X mean that the avalanche left behind. I don't remember what of the two, but you can identify avalanches with being below X mean cross, above X mean cross, and you separate the two contributions that are plotted here. So one is basically erasing the peak, and the other one is basically just contributing to the peak. And these are the avalanches that are overdamped-like, and these that looks more like a shear band are the ones that are more inertial. And in fact, if you measure the fractal dimension controlled by the peak, which basically the fractal dimension of the inertial avalanche, it has a much higher fractal dimension, okay, occupying more space. So this was the work on the inertial avalanches.
Sorry,
yes,
so shear band, to have shear band, you need to have inertia?
No.
Not necessarily,
Not
right?
necessarily.
Okay,
but if you have inertia,
model,
but if you have inertia, you can have shear bands. In fact, even without thinking on the avalanches, if you just go to look to the flow curve, no, a shear band you have when you have this. No? So here you have gamma dot, and typically it's this, as I said, well, log. When you having inertia, it means having a non-monotonous thing here, because then part of this having not inertia, shear band, part of the system will separate, will split, no? Part of the system will deform at this strain rate for a given stress, and part of the system will remain immobile. This is the shear band. So in a similar final element model studying the flow curve that Alexander Nicolas did that, he finds this non-monotonicity of the flow curves and the shear bands. Okay. So, but you can have shear bands by, as I show you in the advertising of the properties of the elastoplastic models, by making the local event durations longer and longer. when you change this parameter in the model, even in the overdamped case, there are shear bands emerging. Okay.
But this is effectively somehow putting inertia, right? If you are increasing the time.
Well, yeah.
Okay, so you need somehow.
But I mean,
this type of
your model
feature.
is still overdamped. When something happens, everyone learns automatically. But yeah, it's like a kind of local weakening or something like this, if you want. I think, yeah, you can think of an effective inertia. So now, this is for completeness, because I'm not going to develop the things, but I want to mention thermal avalanches and avalanches in active matter. So it's just one slide. Matthew already mentioned this, because they are the ones who are doing the first work, I think, on avalanches, on thermal avalanches. Now the idea is that you are not forcing your system, but you have a finite temperature, okay? So as we saw for the pinning and the creep events that were triggered by temperature, etc., well, here in the yielding case, there may be avalanches triggered by temperature. And they say they do an extremal dynamics. Basically, they are just at 0 plus, meaning that the first side that will trigger will be the weakest one always, with probability 1. And then the dynamics should be defined in a way that you have to tune a critical value of X and say, after I trigger the first side, every other side that turns out to be below this XC also yields. If it's above, it does not. Okay? And then, so they do this for different values of X, 0. And then when they arrive to a given value of XC, they find that they have the best power laws and that the functional form for the crossover is holding. Otherwise, they say we are not still critical. Okay? So in the extremal dynamics, you have just a P of X as before, but with this XC, not arriving to 0. And this is shown for different temperatures. Decreasing the temperature, eventually you should reach the XC. Okay, and then they have this distribution of avalanche for different system sizes and collapses. And I think this is in 2D scalar model, and the tau is 1.25. Looked at the fractal dimension is much higher than before, but this is not something strange. It's just because since we are not shearing anymore, we are not breaking the symmetry, and this angle here, you shouldn't refer it to a given orientation. All orientations are possible. So now here the propagator has been randomly chosen. For each event, you have a random orientation of the propagator, okay? The formation can happen in all directions. And then the avalanche become more compact, as before. And, well, with Ezequiel Rodriguez Lopez there, we are working on this problem as well. But now, instead of doing this extremal dynamics, yes?
Sorry. I was curious about
the
fact that DF is larger than 2.
Yeah.
So there's no geometric interpretation of DF as...
Yes, the geometric interpretation is that it's D plus zeta, the roughness. Happens that, okay, well, in this area, we are still not measuring the roughness before, but in the depinning that I show you, I was always referring to the roughness of the interface, and in Quench-Edward-Wilkinson, Quench-KP-Z, etc., etc., etc. In the equilibrium, there were the random bond and the random field disorders with different roughness. Okay, DF is D plus the roughness.
Okay.
So nobody has measured the roughness so far, but we will say it's 0.3 probably here. Okay. Okay, as I said with Heber, we're trying to do the real temperature, not the extremal case. And what is the real temperature? Well, in our elastoplastic model now, blocks will yield instantaneously when they reach the threshold, but also with a Arrhenius probability, they can yield even when they are below the threshold, okay? When still x is bigger than 0. And then they have a certain duration that can be just unity. And we observe similar things, but then we find a temperature after which the avalanche can self-sustain, can go forever. It's like melting the system. And the question is if the critical temperature we are finding, because after this, then it starts to enlarge and enlarge, and you can see that all the sites have been activated. If this TC has some relation with the XC here, because in principle, this is at 0 temperature, but this somehow is creating a final temperature. So while we are in this discussion, in any case, the exponent differ a little bit, 1 to 25, 1, 3. So
just a
yes,
point.
yes, yeah, I come back.
In your, how do you add temperature in the system that you were showing us before? They
In
look
the one
like
of
to be
material
a
and
kernel.
co-workers?
Yeah, I mean, I don't know if the details of, I don't remember the details of this work, but
In our is what is written here. It's very easy. You remember that you have the elastoplastic model, you have the stresses and the ends, which
And-
means
and
that
the
the values of n, the state of the system,
yeah,
or the state of the block, if it's active or inactive.
okay.
So the block is 0. When n is 0, it can only receive stress, but is locally stable. When it overcomes the local threshold, you will say that it fluidizes or activates, and then its stress will go exponentially down due to the fact that the block has been activated, okay? Or
With the
fluidized.
probability that's given by the Boltzmann distribution. That's why.
No, well, okay, and when do you activate? Oh, maybe if I do the drawing, it will be much easier. So this is the stress of the block I. It happens that there is written in terms of x, but it's the same, okay? So this is the stress of the block, and it's growing whatsoever. And this is the threshold that we have set for the local yielding, okay? When it reaches there, then it goes down, okay? And then the idea is that when there is temperature, you can be there, still stable, but a thermal kick takes you up if you want, and then it starts yielding immediately from with a probability that is Arrhenius, okay? So that goes as e to the minus, see, here is the stress difference to the power alpha, okay, which is can be chosen to be different things. I think it is 3/2, but this is like an energy divided by kBT.
And how do you control the temperature? Because you are showing us several.
It's there.
Only there, only in this.
Yeah.
So that's the second part of your stress curve.
Sorry?
Right. That's the temperature. That's in the only. In the, does it depends on the?
No. This exponential decay has nothing to do with this exponential.
Oh. Okay.
This exponential decay is because in the equation of motion for the stress, you have delta sigma or the sigma dt is equal to something that is proportional to the stress when it's on. So minus that, and then it's well. No. This is the probability of activation, the Arrhenius probability of activation. So, sorry, it was not clear. People are also studying, also me. It happens that we haven't finished the work yet, so I'm just showing this picture there. Avalanches in active yielding. What active yielding is? Well, we have a poster and a short talk about this. Very nice. And I'm going to show you here results from this very same group in Chile. Yielding, as we said, I mean, it's produced by shear deformation. But what happens if you, instead of shearing the system, you put activity on the particles? People have shown that actually putting up a little arrow with the infinite persistence, meaning an arrow that you choose randomly at the beginning, but then you keep like that forever, and now having an active force on each particle trying to move in the direction of its own arrow, you can also make this very crowded amorphous solid move. And there is, again, a yielding transition, but now active yielding transition. The flow curves are a mess in the sense that they completely change and have other properties that we don't see in the quiescent systems that or in the deformed system not active. But interestingly, the avalanches show exactly the same statistics. So no matter if you have a passive system or an active system, when you arrive to this plateau of stress as a function of time or deformation, and you do the statistic of the stress drops, you get astonishingly the same exponent, tau, and a very, very similar fractal dimension. Okay? So somehow this is still to be understood, but I mean, I like it because it means, again, that these exponents are universal. They don't even depend on the way you are deforming. That somehow was shown before by Budrikis and Saperi and others in the case where they did not only simple shear, but also compaction, pure shear, etc., and they were getting the same exponent. Okay, this is non-external deformation, it's internal, it's active, but still shows the same. And in the last few minutes, then
Can I ask something very quickly about this part here?
Yes.
Do you expect something important to happen? Well, something important should happen if you change the persistence time instead of being infinite. Bring it down to some lower values.
Yeah. Yeah. So I should have mentioned, but it's written there. People have worked on a mean field version of this problem, and there are analytical solutions. And they have built this quantity that they call the random stress, because when you don't have a preference of direction of deformation, you don't know exactly what stress to compute. And all this works fine and well because persistence is infinite, as in the mean field case. And then this thing is always well defined, and you can measure the stress drop of this random stress and get the thing. What happens until we have seen now, when you have finite persistences, is that, again, this is not a good quantity anymore. And then you have to rely in the Irwin-Kirkwood stress or other things, and you see some differences, but you are not sure if it's because you have to define more cleverly the stress, take into account that there is finite persistence or not, or if it's really a change in the exponent. But I would say that always in a regime, even when you have a finite persistence, if the activity of this stress drop is happening in a time much smaller than the persistent time, you still see the compatibility between passive system and active systems. Then when you start mixing time scales, things can get more complicated. So I want to finish with comments on flow curves that we'll talk more about that tomorrow, but in order to have the complete picture of the criticality of yielding. These are some flow curves in the elastoplastic model literature for different models. Here they were not even fitting an exponent, but okay, here Alexander fitted the one, Lin, Viard, and others, this one. And this is what I was telling to Carolina. Here, for example, you can have non-monotonous flow curves when the duration of the event is large enough with a simple elastoplastic model without inertia, and this system shows shear bands. So we, again, with our 6 models, we measure the flow curves. And remember, we have these 3 taken from the literature. And But all they have in common that when they have been destabilized or when they have the chance to be destabilized because they are above the local threshold, they do it at a rate that is constant. Can be very, very, very big, as here, that as soon as they touch, they go down. But if not, if they will live some time, still this time is as a constant, or stochastically a constant. What is constant is the rate, okay? But we say, okay, well, we proposed this other progressive rate rule which looks more physically, because the site is more likely to yield at it is more overloaded. Let's say it has arrived to here, but it survived, it's still not yielding, not yielding, not yielding, not yielding, and if it goes up here, it should yield immediately, okay? So we propose this progressive rate, and these are a rationale for the analogy with the explicitly disordered landscape that we will exploit more tomorrow. But basically, the constant yielding rate is related to Caspi potential, meaning when you overcome a potential energy barrier that does like a cusp, then you go down immediately to this parabola to the next minima, and this is just a characteristic time. While if the potential is smooth and has these saddle nodes, remember when you tilt the potential, basically you are in a flat region and then you can stay there very, very long times if you don't tilt it more. And it can be worked out at the time when this is smooth, the time it will take to go from one minima to the next one actually will scale with the square root of the, well, 1 over the square root of the difference of stresses, okay? So this is our progressive rule. And now for the flow curves, here are plotted all together. When we do sigma minus sigma c to have, and we put gamma dot in the y-axis and sigma minus sigma in the x-axis to have the values of beta, this is 1 over the n. So to have this shape here, we see that the uniform rates for the 3 models come together here to an exponent 3/2, and the progressive rates for the 3 models come here to an exponent 2, meaning all the other details of the model do not care. But the yielding rule, it does. So we have universality in a way, but this exponent beta is not universal because it depends on the rate rule or in the kind of underlying potential. Well, as a note of color, just the progressive rate, where you have soft potentials and saddle nodes to escape in the phase space from one local minima, etc., seems to coincide better with experiments that, if you remember from the beginning, I told you that they had an Escher-Buckley exponent of close to 0.5. So the inverse is 2, is beta equal 2. So, I mean, if you want to do elastoplastic models to describe some real system, maybe better to use these progressive rate rules. So as a way of finishing, summarizing, we have seen that elastoplastic models for amorphous solids show critical behavior and avalanche statistic that is critical and universal, not depending on details of the models, and they hold scaling laws, etc. And let me say that exponents that we can call static, that they don't have to do with the time or the time, the critical time growing length scale. They are completely universal. Tau, df, phi, for all the models we have the same. Instead, the dynamic exponent, so the Z exponent, which is the exponent of so how the duration of an avalanche of linear size L goes, and beta, the exponent of the flow curve, they depend on the yielding rules. So, and here are the average t as a function of size, so duration as a function of size. So these things averaged here. For the case of the uniform rates, we have a single power law with this exponent. And in the progressive rate, it even induces a dependency, a size dependency of the average time duration for the avalanches. But if you have to fit somewhere, you will fit also an exponent that is different. So Z, and beta depends on the rate rules, and they are not fully universal in the sense. So this is the conclusion. And as I said, amorphous solids undergo this yielding transition that we can define in analogy with the pinning and equilibrium phase transitions. And it has a power law vanishing of the order parameter that is gamma dot as a function of stress. Associated to it, we see avalanches and many critical exponents. And there are some consensus in the literature of a given universality, at least for the elastoplastic models. We have discussed how this changes when you have finite strain rates and you go away from the critical point. Okay, how this affects the avalanche statistics. We have discussed how inertia also can destroy this quasi-static overdamp universal statistics and create new physics. And then we have introduced also this key observable for yielding, which is the density of shear transformation, the P of X, that helps us to understand how the other exponents behave. And also, well, opens a new physics because really this signed propagator, and we can go even beyond the Eshelby. Forget about cosine 4 theta, etc. Now, when you have an elastic kernel or a kernel, interaction kernel that will give positive and negative kicks, will produce these pseudo gaps in the putative chances of blocks to yield or yes, to destabilize. And the pseudo gap then goes in analogy with other very different systems like Coulomb glasses and things like this, where this pseudo gap is also observed. So it's very general. And okay, finally, what I just said, that at least within elastoplastic models, we can have two coexistent universality classes, one for constant rates, one for progressive rates. And the static critical exponents do not depend on that, but the dynamical ones that. And if you are interested on these things, on these models, on these kind of topics, let me tell you that the discussion around thermal avalanches and all what will be the creep of the yielding is open, and there are many people trying to work out that. And another thing is the active yielding, which is also a very, very new field where new works are coming in. So these are two hot topics that you may want to explore. And okay, here there is a list of reference, because I will left these slides for you to have. And with this, I thank you for your attention.
Questions?
Hi, Ezequiel, thank you. In the active case, do you replace shear by the self-propulsion, or do you have both imposed simultaneously?
In this, so you can do both things. In the slide that I've showed you, in this work by Carlos Villarroel and Gustavo Durin, they are only doing either simple shear or self-random force activity. They are not mixing. But in fact, you can, in a model, you can have both on and see how the crossover between one and the other is. It's a bit what we are doing with Roland Weiss and Damian Levis. A different kind of of model. Also, we have not infinite persistence, but finite persistence, so on. But yeah, we are in the mode, let's say, in the middle of the.
So very quickly, there is a paper by Frank Julica from 2 years ago where he has the vertex model, as asked by Danilo. And it's essentially the case without shear, only self-propulsion. And they show that, I mean, they claim it is a new universality class for the avalanches.
Okay, well, yes, I see. I mean, this is a big discussion, no? But in principle, for what we know from this, but there are other, I don't have them in mind now, the references, but this, well, here they show exactly the same exponent, but others have shown very similar ones. But it's open. I mean, it could be that this happened just in the particular dynamical relaxations that they are using here. But I mean, when you want to do things quasi-statically, then you have different choices for the relaxation. And in fact, the poster was showing this, and you gradient descent and others. And maybe if you use another one, they have shown for 2 or 3 cases. Maybe if you go to another case, exponent changes. I don't know. But okay, this is.
Thank you.
Thank you.
Talking about the same topic. It appears the avalanche statistic is the same. So, but dynamical regime shows differences. I was wondering a lot of how isolated avalanches behaves the same, but is it possible that in the collective interaction of avalanches, passive system and active system behave differently, and it would be more collaborative? I was wondering about that. What do you think on that direction?
Well, again, as I mentioned at some point, the only way to define avalanches is in a quasi-static limit. And there, you trigger one side, everything that comes after, if it makes parts of the same avalanche, is causal, and you call this an avalanche. If it's finished, then you trigger something else, and there is no collective behavior of avalanches. The other avalanche is completely uncorrelated with the previous one, okay? And we saw this in the pinning again. In the avalanche of the pinning, of the first lecture, were completely uncorrelated one and the other. Yet, when you are in the creep regime, we had this cluster of creep events that were, they had spatial-temporal correlations. So what will happen here, I think that the avalanches are independent because the protocols are really quasi-static. When you go and you add strain rate and you mix activity with the external deformation, when you have a finite strain rate, you can trigger maybe one avalanche here, while the avalanche is growing and doing its stuff, you keep deforming, and so you can trigger another one there. But you haven't stopped measuring because you are still in the avalanche. So everything comes together to something that is a stress drop. So this stress drop is really an average or resulting from many things that in principle should be separated, but you measure them together because you are at a finite strain rate. So I think that, yeah, when you put in strain rate, you start having dynamical effects in your avalanches that are not avalanches anymore, but they are stress drops. So they are, yeah, can change. Okay.
More questions? If not, let's thank Ezequiel again.
Thank you.
We'll be back at 11.